So I was saying at high school level, you talked about what we call the AP and then a GP, and we called these ones series. And we said, and what is important from here is that you want to talk about the sums. And here, under AP, you said is what we call a sum and also sum to infinity. What you called a sum, it is a sum up to a certain number of terms. Similarly, even up to here, there's what we call a sum and a sum to infinity. Sum you referred to a specific number of terms. That's what you targeted for. Then here, what we are going to do, it is to take what we call the same expression, but now we differ by some small character, which doesn't mean that you covered wrong things, but it implies that you covered a little, but you need to cover more. What we should know that the moment you say it is a series or series, it implies you have to add the terms. We are adding, but what are we adding? We are adding terms of the sequence. That's what it means. What does it mean, therefore? If I have a sequence xn equals to 1 over n, if I try to analyze this much, I'm going to have xn equals to what? I have the first one, which is 1. I have a half. I have a third. I have a quarter, and other terms. Here, if I try to know that this is now my sequence, if I convert this into a series, if I want it to be a series, and this is what I do, then it is a series xn if this one is true, 1 plus a half plus a third plus a quarter. The difference is clear. Then plus other terms. The difference is clear. This is a sequence now because terms are just listed. Now, this is a series because terms are added. And since our interest is to add, there is what we call the summation sign. This is what we call the summation sign. Where it is like this. Just written simply like that. Now, this one here, if I remove this one here, if I take this, I have to clearly explain to you what it means. This is what it means. If I write something like this, then I say that I have my I moving from I is equal to 1, maybe to 4. This is what it means. Or maybe of a certain, maybe sequence xi, of which my sequence can be xi equals to maybe x squared. I'm going to show you how it works. To write this same thing here, this is xn, sorry, or xi. To write this same thing here, I mean that you add for me, it means that you add for me, this is the sequence is xi equals to xi squared. What does it mean? I'm going on squaring. And therefore, if I say I have xi from 1 to 4 of xi, it means I'm going to go on substituting, but these are the values. I'm substituting from I is equal to 1. Then after I substitute in a 2 until when I reach this value here. Then 3, then 4, because the highest is 4. And what does it mean? It means that I'm going to go to x, I substitute x squared plus, this is 2 squared plus 3 squared plus 4 squared. Why am I doing so? Because the formula is telling me go on squaring the x components. That is what it is telling me. And then because of this inner sign, this one here means add for me. This one means from the lower limit. This is the upper limit. This is the upper limit. This is the lower limit. Then what am I? This is the formula. what sits here is the formula. So that is why we have to interpret match this expression. And therefore, if I do say something like this, that sum up for me, maybe before even I write something different, what I may tell you is that when I write like this, from my BR is equal to 1 up to 4 of maybe x squared. This is the same as the same thing of writing from x maybe I is equal to 1 up to 4 of maybe x. This is xr. This is xi squared. It is the same thing as writing maybe n is equal to 1 to 4 of this is xn squared. So what is important is that what you are substituting for this guy here should be the same guy you are putting. So that is the expression there. Now, if I write something funny as like if I write something like this, summing up of n is equal to 1 of up to maybe 3 of this is n squared plus 4n. If I write it like this, now this one is a different thing. It is telling me that put n is equal to 1 here. Here we are substituting this one here. Remember, when you write it like this, we write in terms of a sequence. So this one means substitute for these values, meaning that the same as telling me that I'm substituting for when x is 1, I get 5 plus. Why am I adding? Because of this. When x is 2, this will be 4 plus 8, it will be 12 plus. You go on substituting. When it is 3, you get the value. You add and get the answer. That is the interpretation of the sum sign here. Now, the cell, it implies that we must add. We must add, but the level of adding, depending on what we are adding, may result into many things. But now, specifically, since we are dealing with the sequences, this is what happens. When you take a sequence, when you take a series, then it implies that you are adding. That is the interpretation. But we are adding elements of the sequence. So 3 things happen. Or we result into 3 things. 1, we result into a finite sum. That is the first one. 2, result into an infinite sum. Then 3, we may not get any value. We may fail to get any value. So I want you to read it through page 37. Page 37, that last bit. I'm giving you just 1 minute to read it, and then we move on. That is 3.7, page 37. Hope you have finished. So have you finished, please? Let's try to move on. Let's try to move. Now, we are going to start with a finite sum. Finite sum, after we go to infinite sum, and this is where we shall stop, I think. Now, when we go for finite sum, we should think of many things here. One, that we can sum up squares, we can sum up cubes, we can sum up just numbers, and we have specific formulas. And what does it mean? That if I do like this, if I say that I'm summing from if I say I'm summing from maybe I is equal to 1 up to n of xn, meaning that I'm summing up elements of a sequence up to n. Now, this is finite because I stop on a certain number. But when I do like this, I say summing up from I is equal to 1 up to infinity of xn. This is an infinite sum. I'm summing up to infinity. And then sometimes instead of writing all this, we just say summing up of this is xn, meaning that we are going to go on summing up to when you reach infinity. Meaning that here they are not fixing you, but here we want to fix up to a certain number n. And therefore, because of the high school work we covered, we should now remember three things. One, remember we are dealing with finite sums, meaning that we are summing up to a certain value n. We are not summing up to infinity. The second concept will be summing up to infinity. Now this is if I add 1 plus 2 plus 3 plus, and I add the other elements up to n. You remember from high school or from your previous level, this is the same as n over 2 into n plus 1. So that is the definition. You should know this one from that fingertip, and I hope you have written it down. 2, if I go on squaring this up to this is n squared, I'm to get something which is like n over this is 6 into n plus 1 into 2n plus 1. And 3, if I try to sum up 1 cubed plus 2 cubed plus this is 3 cubed plus others up to n cubed, I'll get something good, which is n squared over 4 into n plus 1 squared. Now, these 3 here, this is a 1, this is a 2, this is 3. They should be at our fingertip. They should be at our fingertip at this point. So, now we need to prove these things here, this formula here, because they are just imported, so we have to prove them. And therefore, if you are to prove, we should remember as we are proving, we have what we call the direct proofs. These are the proofs we have been dealing with, that suppose we have this, then we move up to when we find the last bit. The proofs we have been using in proving some theorems before. Then there is what we call a proof by induction. And this one here, I have not used it before. It's here in this group. So what we do, if you are to prove by induction, remember, we pick element n from n in most cases. So because of that, we start by suggesting, we propose that, or we check for n is equal to 1 in the given formula. Remember, we are using n necessarily, in most cases we are using n, but if it is r, then you use r. If it is p, use p. Then you confirm that it holds. This is the procedure of proving by induction. You prove by induction by checking for 1, then you confirm that it holds. 2, you suppose that it holds for what? For n is equal to k, you meaning that you change the variable from n to k. You call it this, you call this one equation 1. 3, you check or you test if it holds. You test if it holds for n equals to k plus 1. If you do the 3 steps, then you conclude. 4, you make a conclusion. And how do we conclude? That since it holds for n is equal to 1, because remember it's what you start with. For n is equal to k, and n is equal to k plus 1, then it must hold for every k from n or from r or from anywhere they have told you to pick it from. Meaning that it will hold for everything. So that is the conclusion we are expecting. But in most cases, it will be for positive integer, for all integers, but this is the procedure. You prove by induction. You try to check if things are true, but you check at random points. And the random points you have suggested that these are the random points. That's what you are going to take. And let's try to see some examples. Actually, the examples are just simple. We are going to prove the other formula. I'm going to prove 2, but I'm starting, I think, with the first one. Then on the second, you choose which one to do. So for proving number 1, we are proving that 1 plus 2 plus 3 plus up to others plus n equals to n over 2 into n plus 1. This is what we are proving, and it is number 1. And we are using proof by induction. That's what we are using today. So this is a finite sum. And we have said you use proof by induction. So we are going to say check for n is equal to 1. This is n is equal to 1. We substitute in the formula. This is 1. So 1 must equal to, this side we substitute. This is 1 over 2 into 1 plus 1. This indicates to me that I have 1 equals to, this is a half into 2. What does it mean? It indicates to me that 1 is equal to 1. So it holds for n is equal to 1. This is the first one I've finished. We go for the second one. Suppose, when do we use suppose? We use it when you have used the if, meaning that at the back of your head you have said if it holds for n is equal to k. So that's why we are using suppose it holds for n is equal to k, such that we have 1 plus 2 plus 3 plus up to plus k equals to, this is k over 2 into k plus 1. So I've substituted, I've removed the n. Actually, the truth is I've removed the n and I've put k. That is the trick behind it. So this, we said we call that one equation 1. Now after that, we say test for n is equal to k plus 1. This is where the trick is now. Remember, we have it here. We have this is the formula. Now we are adding another term k plus 1 here. And remember, our expression is in k, meaning that it's indirectly the same as using equation 1. And we are going to have 1 plus 2 plus 3 plus. This is k, but we are adding k plus 1. Hope you have seen what I've done. This is what we have been moving with, but I've added another term, k plus 1. It is what I've added there. This one equals to what? Equals to, you see here, we have summed this first bit up to here, and we have called it k over 2 into k plus 1. Now, we are adding this next term, meaning that this addition is the same as plus. I maintain it. This last term is k plus 1. So what are we trying to look for now? We are supposed to show that after you adding this, we should get the same expression as if we have substituted in k plus 1 here in equation 1. That's what we should do. We should simplify this. We simplify this expression to show that this term resembles as if we have substituted in k plus 1. So it is what we are simplifying. So this is equivalent to what? This one and this, we have a common term or factor. This is k plus 1 into, this is k over 2 plus 1. Because I've taken out k plus 1. Hope you can see that clearly. After doing so, I can try to simplify this side, decide that I can have this is the k plus 1 into this is k plus 2 over 2. I'm taking out this a half outside, so this is the same as saying a half of k plus 1 into this is k plus 1 plus 1. Okay, this is the same as k plus 1 over 2 into k plus 1 plus 1. Hope you can see that indirectly, can you see here? Can you see here, please? That this is the expression. This is the expression we are looking for. Or this is the formula we are trying to prove. Now, I've put k plus 1. If I put k plus 1, it implies that this n here, it will be in a position of k plus 1, which is here. Over 2, 2 is a constant, so it will be there. Then what will happen here in the bracket, that this n here now will turn to be k plus 1, which is this guy here. Then this one here will be maintained. What does it mean? Even if you stop at this level, even if you say k plus 1 over 2 into k plus 2, and you stop there, meaning that here it can be seen. If you're a good person, you can easily see that this one here is the same as this. So you are free to just stop at this level, because this one can come before this, and you skip this. Now, remember I have shown the 3, so we have to go to the 4th. Since it holds for k is n is equal to 1, n is equal to k plus k, and n is equal to k plus 1, then it holds for every n coming from n. The reason why I'm saying n coming from n is because this is the partial sum, or this is just part of the sum, part of the set. Actually, what I've done, I've added values, but I've picked them from a set. So it's like a partial set, part of the sequence. So, and therefore, these n's you are seeing, they're coming from this n, because we said these subscripts of the sequence, they come from n. That's why at high school level you used to say for every positive integer, because we said n refers to positive integer. Now go to the what? Go to those two. You choose one I should do for you, then you do the other. Which one can I do?
Do the last one.
I do the last. Okay. Let's see. The third one, because the second I'm sure you can do, you are going to do it as an exercise. That is an exercise 1. So the other link, you are supposed to use the other link to hand in that work. That is number 1 given now. I'm going to give you other 3 so that you hand in. So the third one is 1 cubed plus 2 cubed plus this is 3 cubed plus others up to this is n cubed equals to n squared over 2 into n plus this is over 4 n plus 1 squared. This is the expression here. We are proving by induction. So checking for n is equal to 1, it implies that I have 1 cubed equals to, this is 1 squared over 4 into 1 squared, 1 plus 1 squared. Meaning that I'm going to have 1 cubed equals to, this is 1 over 4 into this is 2 squared. What does it mean? It implies that I have 1 is equal to 1. So it holds. It holds for n is equal to 1. Now we said we suppose the second one. Suppose it holds. Suppose it holds for n is equal to k. This implies that we are having 1 cubed plus 2 cubed plus 3 cubed plus others up to this is n cubed, which is this is k cubed. This is the same as k squared over 4 into k plus 1 squared. And we have called this one equation 1. Now we have said we suppose or we check. We test for n is equal to k plus 1. We have this is 1 cubed plus 2 cubed plus 3 cubed plus up to this is k cubed plus k plus 1 cubed. This equals to what? I'm now going to the other side. Remember, from here to this point, it is n k cubed, sorry, k squared over 4 into k plus 1 squared plus this one here is k plus 1, this is cubed. Now, there is a common factor which is k plus 1. So I'm going to say k plus 1, this is squared. Because squared is the lowest power here, this is to 2, this is to 3. So I have to take it to 2. I get k squared over 4. Then this is a 1 plus this is k plus 1. This is equal to what? This is k plus 1. This is squared. Then this is into. This is k squared plus this is 4k plus 4. This is over 4. Please, this one is simple. You take out to you take the LCM. This is over 1. Then you factorize out of 4 down. I'm sure you can see it. I'm sure you can see it. Don't worry. You'll follow. You move from here to there. You get LCM. This 4 will enter there. This 4 will enter there. This circle will move out. Now, we know, remember, something is good here. If you're having x plus 2 squared, this is the same as x squared plus 4x plus 4. When you check out this, when you check out the one I'm telling you to remember, it is automatically this guy. So meaning that instead of writing this, I'm going to write this, but mine is in terms of k. Therefore, if I take this equal sign maintained, I'll have this is k plus 1 squared over 4. Then into this is k plus 1, k plus 2, but squared. And finally, I'm going to have k plus 1 square over 4 into k plus 2 square. This is the proof, but now we might have to make a conclusion. When you check the other side in the formula, you will see that it is similar to substituting k plus 1 in the formula. So you don't have to get puzzled so much there. So since it holds for n is equal to 1, n is equal to 2, sorry, to k, and n is equal to k plus 1, then it holds for every, this is n coming from n. It holds for n coming from n. So we move on now to something good.